Hello friends, welcome back to this online certification course on watershed hydrology. I am Rajendra Singh, professor in the Department of Agriculture and Food Engineering at Indian Institute of Technology, Kharagpur. We are in module 3, this is lecture number 4 and we will still continue with the streamflow measurement. This is part 3 of streamflow measurement. And in this lecture, we will talk about various hydraulic structures which are used for streamflow measurement and also the slope area method which could be used to determine the streamflow. Now, coming to hydraulic structures, as we know that hydraulic structures like weirs or flumes, they are commonly used for flow measurement in small streams or channels. That is very often you will find anywhere if you go. And these structures offer advantages as they are less influenced by downstream conditions, channel roughness and backwater compared to velocity area method. So, velocity area method has though advantages, but there are certain disadvantages which can be taken care of if we use the hydraulic structures. Coming to the types of hydraulic structures, they may be divided into the 3 categories, that is thin plate weirs, broadcasted weirs and flumes, and there are various in these categories also, and we will discuss each one of them one by one. Now, starting with the thin plate weirs, or which are also referred to as sharp crested weirs, sharp crested or thin plate weirs, and we will first talk about the rectangular thin plate weir or rectangular sharp crested weir. And this rectangular sharp crested weir consists of a flat rectangular plate placed vertically across the stream, causing water to flow over the top edge of the plate. So, as you can see here, this is the channel or stream in which we are, this is the flow direction in which we want to measure the discharge, and this is where this thin plate rectangular weir is installed at the end of the channel, basically this edge of the weir is sharp, where you can see that this is provided an angle of 45 degrees here, and in the and so that the flow, though basically what happens that this plate is something like this. So, what happens that when flow comes here, it doesn't clinch this, doesn't touch the surface, no touching of the surface, and that is why it is referred to as free flow. And then the equations which we use, they are used for free flow, and they are developed for free flow conditions. So, that is why a sharp edge is provided here. The height of water over the weir, which is known as head or stage, it then used to calculate the flow rate. So, here as you can see, this is the head, this is the weir crest which we are calling here, this is the crest here, and then water level or stage above this is H, which is shown here. Typically, this H is measured around 3 to 4 times H far away from this particular stream. So, this direction which basically will maintain distance of 3 to 4 H, and where H is measured. And when B by B is 1, B is the width of the rectangular weir, and capital B is the width of the channel. So, when B by B equal to 1, that is weir is termed as full width rectangular thin plate weir. That means these edges are up to this point. So, the width of the rectangular channel or rectangular channel and the width of this rectangular thin plate weir are the same, then it is referred to as full width rectangular thin plate weir, or it is also referred to as a suppressed weir. And if it is a full width thin plate weir, then the discharge can be calculated using this relationship, where Q is the discharge in cubic meter per second, G is the acceleration due to gravity, CD is the coefficient of discharge, B is the effective width, if it is B by B, then B is equal to B, and H is the gauged head. So, we have to gauge the head here. As we discussed, this gauge is stage is, or the head is gauged at a distance about 3 to 4 times of H itself. And when B is less than B, that means when this is the condition which we are seeing, where the width of the rectangular thin plate weir is less than the channel bed, capital B channel bed, then it is referred to as a contracted weir, and the coefficient of discharge is corrected by multiplying with the contraction coefficient. So, besides the coefficient of discharge, which takes care of the manufacturing issues and also the measurement conditions or experimental conditions. Besides that, a contraction coefficient also has to be used. Just take a simple example. Calculate the discharge over a rectangular weir having a notch width of 4 meter and the approach channel width of 8 meter under a measured head of 1 meter. The CD value is 0.6 and the contraction coefficient is 0.9. So, these are the known values. G we already know, B is given, H is given, CD is given, and contraction coefficient is given. Of course, another thing which is given is the channel width. That is channel width which is 8 meters. So, obviously, because B is less than B, then we have to use the contraction coefficient, and that is why in this equation 2 by 3 CD under 2G BH 3 by 2, as you see here, besides CD, the contraction coefficient is also used for correcting the CD. So, here 2 by 3 CD times contraction coefficient is used because it is a contracted weir, and then of course, the values of G, B, H which we know we are placed here, and then we get the discharge as 6.38 cubic meter per second. So, advantage is that just a single measurement of head gives us the discharge in this case, provided we know the coefficient of discharge. Then other forms of weirs are triangular or which is also referred to as V-notch thin plate weir, and it consists of a flat triangular shaped plate. So, earlier we used rectangular shaped plate, now it is a triangular shaped plate vertically across the stream. So, obviously, as you can see here, the rest of the things remain same. This is the approach channel, the flow is coming this direction, and where we had this rectangular shape thin plate, now we have a triangular or V-notch thin plate placed, as you can see, and the sharp edges are maintained here in a similar fashion. And a V-notch weir has a 90-degree angle. So, angle which this theta, that is this V-notch, this is the angle which we use. This angle is used at theta 90 degrees, and the width across the top is twice the vertical depth, which will quite obvious, because if you have 45 degrees, that means this width is same as depth and either side. So, this becomes twice the depth, and makes it the most commonly used type of triangular weir. So, triangular weir or triangular thin plate weir or V-notch having theta equal to 90 degrees, most commonly used triangular weir. And the formula for calculating discharge by this triangular weir is given here, and it is 8 by 15 CD root 2G tan theta by 2 H 5 by 2. So, CD, G, H already we know discharge measurement or the stage measurement or head measurement remains the same at the top of this V point here, and at a distance of 3 to 4 times H we measure this using a point gauge or hook gauge. We can use, and theta is the angle of notch which we have already discussed. So, most popular one has theta equal to 90 degree, and it is 45 degree tan theta by 2. So, tan 45 degree, which is 1, and V-notch weir is preferred for low discharge channels. So, low discharge channel in the sense, because you know that compared to a rectangular thin plate weir, here because the cross sectional area is less. So, that is why for the same discharge, the value of H will be significantly higher in the case of a triangular weir compared to a rectangular weir. That means it is much easier to measure H. If it is a low discharge channel, it is much easier to find out the value of H or measure H if it is a triangular weir compared to a rectangular weir, because even with the change of discharge, the H value may not change significantly in case of a rectangular weir. So, that is why when the discharge is low in a channel, it's a triangular weir which is preferred. Then and the third type is trapezoidal weir. The third shape which we use is trapezoidal weir, and it has a trapezoidal shaped notch through which water flows. So, the rest of the things remain same, only the thin plate which was rectangular or triangular, in this case it is trapezoidal. So, basically in this case as you can see also, it is a combination of a rectangular notch and two half triangular notches basically. So, basically a sum of a rectangular notch. So, this portion gives us a rectangular notch, and then here to here, here to here, and here to here, if you see, we have half triangle. So, combined together we have a triangle. So, it is a combination of one rectangular notch and a triangular notch, and that is how the discharge over trapezoidal notch is also calculated, like discharge over the rectangular notch plus discharge over the triangular notch, and we have already seen these formulas. So, sum of these two formulae gives us the value of the total discharge through a trapezoidal weir, and already these terminologies we have already seen. Now, as far as trapezoidal weir is concerned, there is a typical type of trapezoidal weir which is known as Cipollati weir, which is a special trapezoidal notch having a side slope of 1:4, 1 horizontal to 4 vertical. So, the weir is free from contraction effect, that is the contraction coefficient in this case is 1. So, that is the advantage of this, but as you can see that because we have to maintain a particular side slope 1:4, so construction requires little bit of care in this case, but Cipollati weir is also quite popularly used in the field conditions. Then we come to flumes, we first go to broadcasted weirs. From thin plate weirs we go to broadcasted weirs, and a broadcasted weir is a hydraulic structure commonly used in open channel flow, and it is type of weir characterized by a wide flat crest that spans the width of the channel. So, as you can see here, this is the crest in this case, this is AB, this is the crest, and it is a broadcasted weir is simply put in the channel and it spans the width of channel, that means its width is same as the width of the channel. And they are preferred in flow measurement due to reduced sensitivity to head changes, lower approach velocity and prevention of submergence. And what happens in this case, they have a typical design such that the flow is obstructed, that means the flow here is obstructed in certain way because it is put in the channel itself. So, the water level rises and the velocity becomes, in this portion, velocity becomes subcritical. And then when the crest comes and beyond the crest there is a free flow kind of condition. So, here it is expected it will be supercritical, the velocity will go up, and that is why it is expected over the crest critical velocity will be formed. So, there will be some critical velocity. So, that critical depth basically we measure here on the crest, and this is the formula which can be used for critical flow because the critical flow occurs. So, in that case if we made the critical depth, this is the discharge equation we can use, that is 1.7 CD LH to the power 3/2, where Q is the discharge, CD the coefficient of discharge, L is the length of the crest which we have seen here, it is the length of the crest here, and H is the height of the headwater and small h is the height of the water over crest. So, basically we made these two measurements, that is the headwater head and height of water over the crest, and then we can find out the discharge using the broadcasted weirs. Then we come to the third type of hydraulic structures, which is flumes, and it is also a flow measurement device which is formed by a constriction in the channel, and the constriction can be narrowing in the channel or hump or both. So, that means if you have a channel, then of course you can have a hump kind of structure, some kind of hump would be used, or if the channel is there, then of course some kind of narrowing of the channel width could be there. So, this constriction could be either by a hump, that is raising the channel bed, or by narrowing the channel width. Both ways it can be done. And flumes offer advantage over weirs, thin plate weir, including continuous flow measurement, capacity to transport sediment, no requirement of loss of head, and minimal risk of submergence issues. So, basically we saw that in the case of thin plate weirs, we had the requirement of free flow, which is not the case in the case of flumes. And there are three popular types of flumes which are used: partial flume, cutthroat flume, and edge flume. Now, let us talk about the partial flume. And the partial flume operates with a small drop in head, adopting to the Venturi principle. That means we will see that there is a narrowing of path, and then that means there is a converging section and there is a diverging section, and because of that Venturi principle works here, and the loss of head is only 25% that of a weir. It comprises of three main parts: a converging inlet section with a level floor. Here you see level floor, and it is here you can see the convergence, and a throat section with a downward sloping floor. This is the throat section here, and as you can see that it is the slope is downward direction, and a diverging outlet section with an upward sloping floor. So, it is a diverging section, as you can see here, and the slope is in the upward direction. So, that means you can see that there is a conversion, there is a diversion, there is a level floor, there is a downward slope, there is a upward slope. So, the construction, as you can imagine, that a construction is little bit typical, and this is how this partial flume looks like. And the size of flume is determined by the width of its throat. So, width of throat is W here, and that basically decides that governs the size of the partial flume. And different sizes of flumes have been calibrated, and formulas and tables developed. So, because all other dimensions here, B, L, G, or whatever we use, all these dimensions are can be expressed in terms of this W, because that's the governing dimension. So, basically these flumes can be standardized, that their design can be standardized, and obviously thus the formula and tables once they are calibrated, they can be developed for these flumes. And the general discharge equation is given in this form: Q equals to KHU, where K is a dimensionless factor which is a function of throat width W, and U varies between 1.5 to 2 and 1.6, and H is of course the head, which is being measured here just in the beginning of the converging section. So, this is the typical drawing of this is how typically a partial flume looks. Now, we come to cutthroat flume. The name itself suggests the cutthroat flume is an attempt to improve the partial flume by simplifying the construction details, because the constructions were a little bit complicated. So, that is why this has been taken care of. And this cutthroat flume has a flat bottom converging and diverging sections and zero length of throat section. So, throat section is eliminated here or cut, and that is why the name cutthroat flume with reference to the partial flume. And it is unlike the partial flume, where we had flat converging section, but at sloping upward diverging section. Here it is flat throughout. This is flat throughout, and it can operate either as a free flow or a submerged flow structure. So, both are possible in this case. And as you can see here, this is the W, this is the where throat width was there. Here it is just at the joint of the conversion and divergence section, that is W, and then all other dimensions are put in terms of W or L, where L is the length of the weir. So, the general discharge equation is given in this form: C1 H1 HAN times L, where C1 is a free flow coefficient, H is the upstream depth of flow, which is measured here, and N is the exponent whose value depends on the flume length. So, flume length already we have seen, this is flume length, and most of dimensions are expressed in terms of W and L. So, W and L if we are decided, then all other dimensions can be found out, and then we can find out we can measure H here in the upstream section and can use in this equation. And it is economical and easy to construct H compared to a partial film, which is quite obvious because the design is very simple. And of course, the cut short section is also taken away. So, that is why it is a little bit economical also. Then we approach the slope area method, and the slope area method is a common technique used in hydrology to estimate the discharge or flow rate of a river or a stream, and it consists of estimation of cross sectional area and slope of the energy gradient in the reach. And basically it is based on the energy principle. So, the energy equation for a reach of non-uniform channel is given by this relationship. So, basically here we select a channel reach, that is upstream section, that is section 1, upstream section, and section 2 downstream section, and at the distance of L, and then of course, we have to have various measurements in order to be able to use the energy equation. So, energy equation we know is Z1 plus V1 square by 2G is J2 plus B2 square by 2G plus HF, which is nothing but the loss of energy, the energy loss between section 1 and 2 HF. So, HF can be calculated from this relationship in terms of Z1 V1 and Z2 V2. And the energy slope, which is nothing but HF by L, can be then calculated by HF is here, L we know. So, the energy slope S can be calculated in this form. So, Z1 is elevation of water surface at section 1 above a common datum. So, some datum has to be chosen. Z2 is elevation of water surface at section 2. V1 is the mean velocity at section 1, V2 is mean velocity at section 2, G is acceleration due to gravity, and L is the length of. And so, basically as you can see here, this is nothing but the velocity head V1 square by 2G, which is being considered here. So, basically it is a energy conservation principle which is used between these two sections, and from there the energy slope can be obtained. There are certain assumptions behind slope area method. So, that the flow is steady uniform, that is the method assumes that the flow conditions, that is velocity, depth and discharge at any given point in channel do not change over time, and these conditions are constant along the length of the reach. So, that is a important assumption. Then next assumption is related to applicability of Manning's equation, that is the slope area method typically employs Manning's equation to relate flow velocity to channel geometry. So, this assumes that the flow resistance is adequately described by Manning's roughness coefficient, which may not always be case, especially in channels with complex geometry or vegetation. So, of course, this may not be true, but this is the assumption that this method can be used only in channels where Manning's equation is valid. Then another assumption is negligible sediment transport. The method assumes that sediment transport does not significantly influence the cross sectional area of flow. In channels with high sediment transport rates, this assumption may not be valid. So, that's one caution that one should not use this method where there is a lot of sediment transport. And of course, this is only applicable to open channels, that is primarily applicable to open channels where the water surface is exposed to atmosphere, and this method may not be suitable for enclosed conduits or pipes where flow is under pressure. So, where the flow is under gravity, then only this method is applicable. Now, coming to computation of the discharge, if the channel is straight, comparatively narrow, and the slope of water surface is essentially uniform, then the discharge may be calculated using Manning's equation, that is Q equals to AV, that is, and V is 1 by N R to the power 2 by 3 S by 2 power half from Manning's equation. So, it is 1 by AN, A bar, A R to the power 2 by 3 S to the power half, where A bar is the average cross sectional area of the channel, that is average of two sections. R is the hydraulic radius of the channel, which is A bar by P, where P is the weighted perimeter of the channel. S is the bed slope of the channel, H by L. H is the fall of water surface over the length of the river reach L, and N in the Manning's roughness coefficient. And in this case, this particular term A 1 by n, A R2 power 2 by 3 is also called conveyance. That comes from hydraulics. If you have read hydraulics, you already know that this is the conveyance of this channel. A 1 by n, A R2 by 2 by 3 is called the conveyance of the channel. Now, this is besides this, the US Geological Survey has suggested a simple logarithmic model for the computation of discharge in cubic meter per second for uniform channel section area, that is A bar in square meter, and this is a relationship, that is log 10 Q is 0.191 plus 1.33 log 10 A bar plus 0.05 log 10 S plus 0.056 log 10 S square. So, S is the slope and A bar is the area, which we already know. So, we can directly use this US Geological Survey equation also for finding out the discharge. Now, if the flow is non-uniform, that means if the cross section changes, then the average conveyance is estimated, that is K is K1 by K1 times K2 is square root of K1 and K2, where K1 and K2 are conveyance. Already we have seen conveyance is 1 by n, R to power 2 by 3, S to the power half is nothing but the K. So, conveyance is two sections are calculated and discharge is given by this relationship. So, K1 K2 times S, where S is the flow. When the flow is non-uniform, the discharge estimation includes a trial and error procedure for adjusting the velocity head, and we will see that through an example. Let us take one simple example. First, that compute the stream discharge through a uniform straight river reach of 200 meter length by using Manning's and USGS equations. The upstream cross sectional area is equal to the downstream cross sectional area of the channel, which is given as 120 square meters. So, it is a uniform section. The fall of water surface is 0.15 meters. The weighted perimeter and the average depth of water flowing through this channel are 60 meter and 2 meter respectively, and Manning's roughness coefficient value is 0.03. So, it is a uniform cross section, and that means Manning's equation can be straight away used. So, average cross sectional area is given as 120 square meters, weighted perimeter is given as 60 meters. So, the hydraulic radius R A bar by P comes out to be 2 meters. Fall of water surface H is given, length of river reach is known. So, bed slope S H by L can be calculated at 0.00075. And Manning's roughness coefficient is also given at 0.03. Since the reach is straight and uniform and the cross sectional area is similar, the stream discharge can be computed by Manning's formula. That is, here using directly Manning's formula, we can find out that discharge comes out to be 174 cubic meter per second. But because it is a uniform section, so we also have an option of using the USGS equation for the slope area method by using this logarithmic model. So, here we know A, we know S, both things we have calculated. By putting this in the model, we get USGS is 177.83 cubic meter per second. As you can see here, by Manning's equation, we got 174. With this model, we got 177.83. So, pretty reasonable close values we get by these two methods. Then let us take an example, a little bit complicated one. Compute the stream discharge through a straight river reach of 200 meter in length. The upstream and downstream cross sectional areas of the channel are 1231 square meter and 1222 square meter. The fall of water surface is 0.3 meters. The weighted perimeter for upstream and downstream of channel are 320 meters and 310 meters respectively, and the Manning's roughness coefficient is 0.03. Now, because in this case the channel cross section is non-uniform, we need to use the iterative procedure for adjusting the velocity head. So, initially we know A1 cross sectional area upstream weighted perimeter, upstream hydraulic radius. So, A1 P1 is known, R1 can be calculated. Similarly, downstream cross sectional area and weighted perimeter is given. So, we can calculate the downstream hydraulic radius also. And now, the fall of water surface is all over the reach is also given, and length of river reach is also known. So, we can calculate the bed slope of the channel, and Manning's roughness coefficient is given. So, that means in this case we have to calculate the conveyance for upstream section and the conveyance for the downstream section K1 and K2 by putting the values in these two equations 1 by n A1 R1 2 by 3 and 1 by n A2 R2 by 2 by 3, and we get two values 1,0787 and 1,01,603. And then we can use this relationship Q equals to K1 K2 S, and putting these values we get the discharge is 3919 cubic meter per second. But this is the first approximation of discharge, and we have to make the velocity adjustment. So, obviously, we will go to second approximation. That means, we will calculate the velocity head using the new discharge, the discharge just now we calculated, and the velocity head comes out to be 0.516, and its downstream section comes out to be 0.524, and the difference in the velocity head is 0.008 meters, 0.008 meters. So, adjusted fall can be calculated. That earlier the fall was 0.3. Now, we have found that with new discharge there is adjustment. So, H adjusted is 2.292, and that means the new slope comes out to be 0.00146. And the updated discharge we can calculate at 3,869 cubic meter per second. The third approximation, because we have to continue this trial and error procedure unless the two discharges are same. So, we will now go with this iteration with the new discharge Q equals to 3869. The procedure remains the same. We will calculate the velocity head, we can calculate the velocity head difference, and the adjusted fall in this case will be 0.3 minus 0.007, which comes out to be 0.293, and so new slope we have to calculate, and then we have to calculate the new discharge, which comes out to be 3870 cubic meter per second. So, with this we go to next approximation again with this Q equals to 3870, and we calculate velocity head at section 1, velocity at section 2, the velocity difference which comes out to be 0.007, and we get the H adjusted and S new, which again comes out to be 0.0014, and the discharge comes out to be 3870. So, now if you remember, the Q here is the same as that in the third approximation. So, the procedure will terminate here with the discharge measurement is 3,870 cubic meter per second. So, with this we come to the end of stream flow measurement. We have seen all the direct and indirect methods, and thank you very much. Please give your feedback and also raise your doubts or questions which can be answered in the forum. Thank you very much.